Right, so just to clarify, this is not on syllabus. This is just for those of you who are interested in seeing where this comes from. So I've done a slightly different version of the drawing here. So what you've got to imagine is these straight lines x, y, and x, they often say x primed or x dash. So x prime, y primed, those lines are wavefronts. So those are showing how the wave is coming in to this boundary. The red arrows are showing the direction. You can see it's changed direction because it's changed speed. I've also marked on there θ1 and θ2. Those are the same θ1 and θ2 as we had before. Think of a bit of geometry as to why those are equivalent to the other angles, but they are, so just take my word for that. Okay, now we can actually write down a few things here, because I'm going to say that my top material here, N1, and bottom material, N2. So if I think about in N1, all right, I know that the speed of light in the substance N1, so I'm going to call it CS1. Thinking back to my original formula for refractive index, is going to be C over N1. So that's just rearranging the N1 equals C over CS. And similarly, CS2 is C over N2. Okay, we're going to need those a little bit later on. All right, now we can also say, let's just imagine what's happening in the time it takes the wave at x to move to x primed. Right, so imagine actually going back to our truck. As our truck, this is sort of the case where this wheel has hit the new material. And so in the time it takes this wheel to go from x to x primed, this other wheel has gone from y to y primed because of the 2 points that we've picked. And so if we call that time t, we know that x primed, so that's this distance, well, distance equals speed times time. So the speed of the light here is cs2 times time. And similarly, y primed on this side is cs1 times t. Okay, we'll come back to those in a sec. Right, just using a bit of trigonometry, a bit of SOHCAHTOA. Sine θ1, well, opposite over hypotenuse. So opposite here is y primed. Hypotenuse is this line here, xy primed. So it's y primed over xy primed. Sine θ2 is then, by the same argument, x primed over xy primed, because it's this same central line, xy prime. That's the hypotenuse in both of those triangles. Now, we can combine these together, because if we think about this, this would say that xy primed equals y primed over sine θ1, and that must equal, well, from this equation here, xy primed is x primed over sine θ2. Okay, now what I'm going to do now, just to make this a bit easier, I'm going to cross multiply it all. So I've got y primed times sine θ2 equals x primed times sine θ1. Right, y primed we had from up here is cs1 times t times sine θ2 equals cs2 times t times sine θ1. Now, we can straight away actually cancel the t's from both sides. Okay, the t cancels. Now cs1 from up the top here, look, was c over n1 times sine θ2 equals cs2 c over n2 times sine θ1. Okay, c's cancel. And so if you now imagine cross multiplying, so multiply both sides by n1 and by n2, okay, and we're slightly running out of space here, let me just put that there. Okay, if we now multiply across, you can see that n2 times sine θ2 equals n1 times sine θ1, which is Snell's law. As I say, that's above what you need, but it's just there in case you're interested. Okay, right, well, I will see you on the next video where we're going to look then at total internal reflection.